In a previous lesson, you learned how to solve a system of equations by graphing. In this lesson, you will learn an alternative method for solving a system of equations by using what is called the substitution method. Now here we have a system of equations. We have two equations, both of which have an x and a y in them. And our objective is to solve without graphing. Alright, so to do this, we can pick one of the equations. And let's pick the first one, and we can solve the first equation for one of the variables. So we're going to choose the variable y just because. So solve the first equation for y. So given x plus y equals 4, I can solve for y by subtracting x from both sides. Okay, when I do that, I have y equals, and it's going to be 4 minus x. So that is step one. Pick an equation and solve it for one of the variables. Step two is I take this new answer, the equation I solve for, and substitute it in place of equation 2 for that variable I solved for. So we see here equation 2, and we solve for y. We can replace that y with what we solved for, with what we got. So we got 4 minus x, plug that in for y. So we have, instead of 2x minus 3y equals 13, we now have 2x minus 3 times 4 minus x equals 13. So then I can solve this. I have negative 3 times 4 is negative 12, and negative 3 times a negative x is a positive 3x. So I have 2x plus a 3x, which is 5x. So 5x minus 12 equals 13. Solve for x by adding 12 to both sides. We now have 5x equals 25. And then divide both sides by 5. Now we have x equals 25 over 5, which is equal to 5. So when I substituted the y with a 4 minus x at this point right here, this worked well because now we're down to just one variable, which we have worked with a lot in the past. And now from here, we need to figure out what is y. So we're halfway done. So we found x, we just need to solve for y. So I can pick either equation, and in this case, the first equation will be easier. So I can pick the first equation, and I plug this 5 in for x, and then I solve for y. So instead of x plus y equals 4, I plug a 5 in for x, so now I have 5 plus y equals 4. Solve for y by subtracting 5 from both sides. We now have y equals 4 minus 5, which is negative 1. So x is 5, and y is negative 1, which I can write as an ordered pair, and that would be 5, comma, negative 1. So what I've done is I have found where these two equations will intersect without even needing to graph either equation. So notice this method could be simpler, especially if you start dealing with fractions. And by the way, we want to always check our answers. So here we have 5, negative 1. We can check it by plugging it back in to both equations. So here's 5, negative 1. Plug it into the first equation. We now have 5 plus negative 1, which gives me positive 4. So 4 equals 4. That is true. So it works for the first equation. Plug it into the second equation. So we have 2 times 5 minus 3 times negative 1. We have 10, and then negative 3 times negative 1 is a positive 3. So 10 plus 3 would be 13. So 13 equals 13. That is a true statement, which means we do have the correct answer. Here is another example. We have 3x minus 2y equals 10, and x plus 2y equals 4. So again, to begin, I need to solve either equation for one of the variables. And a little trick is I want to look for the variable with no numbers in the front, if possible. So sometimes that is not the case. Sometimes you'll have every variable with a number in the front. But notice here, the second equation, there is no number in the front. It's an assumed 1, right? So let's solve that second equation for x. So we have x plus 2y equals 4. Solve for x by simply subtracting 2y from both sides. Now we have x equals, and it's going to be 4 minus 2y. So from here, I can then substitute this in place of the other equation, 4x. So looking at that first equation, 3x minus 2y equals 10, in place of x right here, I can put in the 4 minus 2y. So at this point right here, we now have one equation with just one variable. So it's not x and y anymore, now it's just y's. So I can solve this. I can begin by distributing the 3. 3 times 4 is 12, and 3 times negative 2y is negative 6y. And then the negative 6y can combine with the negative 2y to get negative 8y. And then to finish this off, I can get rid of this 12 by subtracting that over. We now have negative 8y equals negative 2. And then divide both sides by negative 8. We now have positive y equals a positive 1 over 4. So I have solved for y, and now I just need to figure out what is x. So to find x, I can plug 1/4 into either equation for y. And again, I want to pick whichever one will probably be the easiest to work with, which in my opinion is going to be the second equation. So if I plug a 1/4 into that second equation, we now have x plus 2 times 1/4 equals 4. So in place of the y, I put a 1/4. So then 2 times 1/4, that is the same thing as 2 over 1 times 1 over 4. 2 and 4 we can divide, we get 1 over 2. So 1 times 1 over 1 times 2 is 1 over 2. So I have x plus 1/2 equals 4. To solve for x, I can just subtract 1/2 over. So the 1/2s will cancel out. And I have 4 minus 1/2, which would be 3.5. So my solution is x is 3.5, y is 1/4. I can write that as an ordered pair, and it'll look like this. So notice, again, that we do not need to graph to find where these lines intersect. This is our solution. And if we were to graph this, it'd be very difficult to get this exact answer because of the fractions. So that is why this method is preferred than graphing, because we get a more exact answer. And we can always double check our answer by plugging this back in to both equations. So using that point, plug it into the first equation, we would have 3 times 3.5 minus 2 times 1/4. And notice I converted 3.5 to an improper fraction because that's going to make it a little bit easier when I multiply. So 3, or 3 over 1, times 7 over 2 would give me 21 over 2. Then 2 times 1/4 is the same thing as 2 over 1 times 1 over 4. 2 divided by 4 would give me 1 over 2. So I have minus 1 over 2. So 21 minus 1 gives me 20 over 2, which would equal 10. So this one works, and we need to check now for the second equation. Here we see x plus 2y equals 4. Plug in 3.5 for x and 1/4 in place of y. I kept this as 3.5 in this case because we don't need to multiply 3.5 with anything, and it's going to be easier to just leave it like this for this equation. And then 2 times 1/4, we've already mentioned, is 1/2. So we have 3.5 plus 1/2 equals 4. So 3.5 plus 1/2 is 4. So we have 4 equals 4. That is a true statement, which means we have the correct solution. Now I'm going to finish by showing you 2 more examples, both of which are special cases. So here we have another system to solve. X minus 3y equals 6, 2x minus 6y equals 11. So to begin, I want to pick an equation and solve for one of the variables. Notice this x right here has nothing in the front. This is going to make x to be the best choice to solve for. So let's pick equation 1 and solve for x. So we have x minus 3y equals 6. To solve for x, we simply add 3y to both sides. Now we have x equals 6 plus 3y, or 3y plus 6, same thing. Now step 2 is I want to use the second equation and plug in 3y plus 6 in place of x. So here in place of x, I'm going to plug in the 3y plus 6. And then from here I can solve. So I now have 6y plus 12. And then the 6y minus 6y, those will cancel out, and that gives me 0. So I'm left with 12 equals 11. Okay, notice this is unique because there is no variable anymore. What we have is a false statement with no variable, and what that means is that there is no solution. And what that would also mean is that what we have is actually two lines that are parallel. So if you were to graph this, we would have two parallel lines that never intersect. So therefore, there's no solution. And we can see that without graphing by looking right here at this false statement. So if you see a false statement like this, we know that it's going to be a set of parallel lines. Okay, one more example. What if you had y over 3 equals 4 minus x, and 3x plus y equals 12? Well, to begin, I would like to solve one of the equations for one of the variables. Now here, I'm going to choose this first equation to solve for y, and the reason is because of this fraction y divided by 3. All we have to do is multiply both sides by 3, and that would solve for y. So let's pick that first equation, solve for y, and so multiply both sides by 3, and on the left side, the 3's will cancel. On the right side, multiply by 3. We would have 3 times 4, and 3 times negative x. We distribute. So we have 12 minus 3x. Okay, so from here, I want to use 12 minus 3x and plug it in place of y into the other equation. So we plug it here in place of y to get 3x plus, and then 12 minus 3x. Well, with the plus sign, the parentheses you can just ignore because we're adding the 12 and adding a negative 3x, which would just be 12 minus 3x. And here, 3x minus 3x gives me 0. That cancels out. So I'm left with 12 equals 12. So again, this is unique because there is no variable left over, and we just have a number equaling a number. Well, in this case, 12 equals 12 is a true statement, and what this means is that we have an infinite number of solutions. So if you see a false statement, like 11 equals 12, that is no solution. If you see a true statement, such as 12 equals 12, that would be an infinite number of solutions. And graphically speaking, if I were to graph both of these equations at the same time, what we'd get is one line on top of the other line. So we have two lines on top of each other, which means that there's an infinite number of solutions. So this substitution method is a second way to solve a system of equations. We have the graphing method, which has disadvantages and advantages. And a key disadvantage is when you have a fraction as your answer. Now, substitution, on the other hand, also has some limitations. The biggest limitation is if you have a lot of fractions in the solving process, it can be a pain to try to solve using this method. Because with everything we've seen in this lesson, we've had at least one variable with nothing in the front. For example, like the x plus 3y equals 4, then maybe like 2x minus y equals 6. If you had something like this, okay, there's nothing in the front of this x, right? And actually, let's make this a 4. So let's say we had this example. There's nothing in front of the x, all right? So this makes it easier to solve with the substitution method. Now, what if you had a number in front of everything, like 5x, and 3y, and 2x, and minus 4y? Okay, if you have a number in the front of everything, it makes it really messy at times trying to use the substitution method. So in a later lesson, we'll introduce to you a third technique for solving systems of equations. But for now, this will conclude our lesson for today, and we will see you next time.